So thank you very much for giving me the chance to tell you a little bit about some work I've been doing initially in collaboration with Arkady Zeitlin, and then a bit by myself, and more recently with Alessandro Torielli, who's also at MIT. So the background, or the starting point, is the relationship between the Landau-Lifshitz equation and the ADS-CFT correspondence, and this was, I guess, first noticed by Kruczynski, who told us that in the continuum limit of the SU2 one-loop dilatation operator, so if you take the SU2 dilatation operator and you consider a very long spin chain, and say the sites of this spin chain come closer and closer together in some precise meaning, that this system is governed by the Landau-Lifshitz equation. So I first write this equation in this form because I think this is the form that is most familiar. You've got a free vector which is on a sphere. There's a time derivative, first order, second order in the spatial derivative, and there's epsilon ijk. A form that's slightly more useful of this equation is if you just redefine the ni's in terms of a complex vector field with two components now again squaring to 1, and then the Lagrangian takes this simple form. You've got a kinetic term with a U1 gauge connection, and you've got this Vezzumino or potential term. And the way this was originally obtained was by taking the expectation value between two coherent states of the dilatation operator, and at each site of the spin chain, there are j sites, you have a coherent state for SU2 mod U1. So the first thing I'd want to say is that you can ask the question, well, what happens? Can you write down the Landau-Lifshitz equation more generally, let's say? And obviously the answer to that is yes. And the way you would go about doing that for a general coset is if you give me a coset G mod H and a particular representation lambda, then you can go to the book by Perewomov or any such thing, and they'll tell you the exact circumstances under which you can construct a coherent state. And the main thing that you really need to do that is, in this representation, you need a vacuum state such that any element of the subgroup H acts by a phase on, it is represented by as a phase. So if you have such a state, you can easily write down the Landau-Lifshitz sigma model, which looks like this. So this part here is sort of very familiar. It looks very much like a sort of principal chiral model on G mod H, spatial part of it. And here is this Vezzumino term. So this is a H covariant derivative, and this is just a normal derivative. And in particular, if you want, you could do this for this supergroup coset, which is the one that's relevant to the one-loop dilatation operator, Weiser's one-loop dilatation operator. And there's in the paper, I have a more explicit realization of this Lagrangian in terms of some fields on this coset. But so these sigma models, I think, are quite nice. They somehow are supposed to tell us about the weak coupling, description of the gauge theory. The exact way in which they do that is not entirely clear, but they certainly should encode the anomalous dimensions of the dilatation operator. And they have a number of sort of, let me just list quickly some of their features. So first of all, there is this local H invariance. So that was, so you've got this gauge symmetry H, and that was kind of obvious for the for this part of the Lagrangian because it's just an H covariant derivative. But here you can also show that up to a total derivative, this term is invariant with respect to local H transformations. They also have a global, they are also invariant under global G multiplications, this time from the other side. And so there are some Nefer charges, and I've written down the current here. Another thing that's quite nice about them is that you can write down some bilocal conserved charges out of these currents. So if you take the tau component here and you plug it in, and this integral is, I'm not sure if my handwriting is particularly legible, but it's done not from -infinity to +infinity or 0 to 2 pi, but just up to sigma. So, and it's a double integral. And finally, one other nice thing is that you can show that there's a lax representation for all these models. Okay, so, well, one exercise that can be done is to compare this Lagrangian to some large charge limit of the Green-Schwarz string. And the motivation for this is that we know that at order lambda, in the large charge limit, the string energies agree with the anomalous dimensions of the gauge theory operators. And what has been done in the past is that you could have taken a bosonic subsector of this Green-Schwarz Lagrangian gauge fixed and take some large charge limit, and you end up with one of these bosonic Landau-Lifshitz models. On the other hand, this proved to be a much trickier technical problem if you wanted to include fermions. This is because it wasn't clear how to fix kappa symmetry. So in the Green-Schwarz string, you've got kappa symmetry, and if you fix it badly, then you're going to end up with some fermionic variables, which you then might have to redefine in some particularly complicated way to relate them to Landau-Lifshitz variables. So what I want to tell you a little bit about is how you can fix this kappa symmetry in a particularly natural way. And the way that story goes is I'll show you that there are some subsectors of the Green-Schwarz superstring which have a large number of non-zero fermions. And in these subsectors, it's possible to quite easily define a suitable large charge limit which reduces to the corresponding Landau-Lifshitz model. And so that'll teach us what are the most natural what is the most natural kappa gauge to pick for the Green-Schwarz string from the point of view of a dual gauge theory, so to say. So the reason we somehow will circumvent this question of kappa symmetry is a curiosity, because what happens in these subsectors is that even though you have kappa symmetry, it acts trivially on shell, and so you never really have to fix this gauge symmetry. So that's somehow just an amusing fact, and I'll tell you a little bit about that now. So to say what are these fermionic subsectors, I just put my transparency this way so that it all fits on one line. So there's the Metz-Zeitlin coset, and I write a sort of inclusion here because the top is always included in the top and the bottom in the bottom. And what is more, the Z4 grading that we have here that's used to construct the Green-Schwarz action is exactly the same as the corresponding. There are Z4 gradings here, and they're all exactly the same. So they're all restrictions of one another. Now, what that tells you is that actually that these are strictly truncations, consistent truncations of the Green-Schwarz action, and you can easily count what fields you have in that, and all three of these have got two bosons, one if you want from the ADS part and one from the S5 part, and they contain 4, 8, and 16 fermions. And since you inherit this Z4 grading, well, you get this nice form of Green-Schwarz action that Nathan and collaborators came up with. So you know the action in these models. And just to sketch now an idea of why these models don't really have kappa symmetry, on shell at least, I'm going to show you how that works in the case of a superparticle on the simplest coset here. So the story is exactly the same on all these supercosets, but here I can write down the action in a very closed form, and it's very simple, and it just fits on one transparency. So for the case of a superparticle, well, of course, we let our action not depend on sigma, so we don't have a Ves-Zumino term, and the action is simply this. There are two bosonic fields, phi plus, phi minus. There are two complex fermions, eta 1, eta 2, and their complex conjugates with index upstairs. And there's this Einbein on the world line. And you can show that kappa symmetry on these fields acts in this particular way. And what's important to note is, so I've defined this little a here. I'm sorry for introducing so much notation, but it's just to simplify. The action really is very simple. It's just Einbein times derivative of field times this mess. And we don't really need to know very much about what this mess is, except that when you do the variation of the fermions under kappa symmetry, so these are your kappa parameters, this A comes up front. And you can show that this action is invariant under this variation with a local parameter kappa in the usual way. But the point is that if you look at the equations of motion of the reduction of the Virasoro constraints for the Einbein, those tell you essentially that A has to be equal to 0 on, and so on shell, the kappa variation of the fermions here is trivial. So this is why and it goes through in all three of these models in exactly this way. There's always this factor out front, which is 0 on shell. So that's why we can avoid answering the question about how to fix kappa gauge. So what I want to say now is that, okay, you should start with a Green-Schwarz action now and take some large charge limit and end up with a Landau-Lifshitz action. And I'll show you how that works again in this very simple setting, just so that the formulas are short. And because we are able to do this, then for all three of these cosets, and the last of these cosets contains 16 fermions, so it contains all the fermionic degrees of freedom that this theory originally has, well, then that'll show us the right identification of what are the good fermions to map to the gauge theory. So here's the string action for the Green-Schwarz action for this coset. And this action was first written down by Olde, Arutyunov, and Frolov, who conjectured that this is a consistent truncation of the Green-Schwarz Lagrangian. I think they looked very hard at some cubic couplings, and they saw that they were not there. But there's as I explained, there's a very simple group theoretic reason for this. And so this first term here we met before in the superparticle case, and there's a Vezzamino term. And to cut a long story short, what you find is that there's a solution to this. The complete solution to this action involves phi plus equal to kappa tau, and this first fermion has this expansion where this is just the usual BMN formula, n squared plus kappa squared, and the remaining fields phi minus and eta 2 are fixed by equations of motion. So finally, if you take here you can define the large charge limit to be taking k to be very large, and then you end up with an expression which is written in terms of two fermions, the functions of tau and sigma, and these fermions satisfy this Landau-Lifshitz equation precisely for this coset model. So this is somehow very simple because everything is quadratic once you pick this solution, but the story goes through in pretty much the same way for these larger cosets. Okay, so I think it's a good point to summarize. What I've told you about is how to construct general Landau-Lifshitz sigma models. We've identified on the string side fermionic subsectors which have trivial kappa symmetry, and we've been able to take the large charge limit for these guys and map them to the corresponding Landau-Lifshitz sigma models. And this teaches us what is a good kappa gauge from the point of view of gauge theory. And I think this is precisely the kappa gauge that people have been using. I guess Jan and Sergey and Maria and Gleb have been using in their calculations. But here there's perhaps a sort of simple motivation for why this gauge is useful. Thank you. Well, I think if you turn on some dilaton, then you should be able to.
What's the argument? Why do they have consistent? If they're supposed to be consistent conformal field theories, these truncated Lagrangians.
I think they're supposed to be consistent string theories.
I'm sorry? No, they're not.
Well, they're supposed to be consistent string theories, I guess, because you can turn. Well, if you turn on a suitable dilaton, you can. Well, just because I could tune my dilaton in a suitable way to compensate for any anomaly that I have from the fields, right? It's not going to be a nice string theory in any sense, but.
You might get the central charge to it, but I don't think it's enough.
So Well, I could fix the beta function problem in this way by turning on the right dilaton. I guess that's all I'm really saying.
There is no, I don't know any argument why this truncation should be consistent. It's quantum theory.
So maybe we can. Well, maybe I can discuss that at the end.
My question?